Welcome you to this lecture on marine hydrodynamics. Today we will talk about wave transformation and energy relations. So, there are various transformations when it comes to waves. So, here we will emphasize two things, one is the scattering and radiation. And the other one is called radiation. So, what I mean, I will also, if time permits, I may talk a little about refraction, if not today, maybe in the next class. So, what I mean by scattering, before that let me talk about three waves. What I mean by incoming wave and outgoing waves. In case of incoming waves, suppose we have a observer here. In case of incoming wave, the wave approaches towards the observer or towards the obstacle, whatever it is. It can be approaching from either direction. On the other hand, when it comes to outgoing waves, the wave that moves away from the observer or the obstacle. So, these two are the incoming waves and these two are the outgoing waves. So, now based on this we will define what is scattering and then what is radiation. In case of radiation, what we do that this obstacle, it only radiates energy, basically radiates the wave. That means only from here. Initially there was it was like a calm water, but this obstacle, it generates the wave and it oscillates or vibrate. So, in the process, because of this it generates the wave and only energy is radiated in both the direction, and then we call this as the outgoing. There only outgoing waves exist. Here we will have only outgoing waves. So, that is happen in case of a problem of radiation. So, that one process. So, here the obstacle or the structure which oscillates, and it sometimes we call it a wavemaker problem, means the wavemaker problem or problem of radiation. So, in this what happens, this generates the wave and the energy wave, because of its oscillation it generates a wave and this wave goes away from the obstacle. So, in this case, and often we call this either the radiation problem or the wavemaker problem. Like on the other hand, in case of when it comes to the scattering problem, here what happen, here you have an obstacle, an incoming wave will be approaching to this obstacle. So, suppose this is the bottom domain, this is the free surface, and because of this obstacle what will happen, because there is a gap between here and here. So, a part of the energy will be reflected back, and because we have gaps, so a part of the energy will be going out in this way. So, there is a transmission of energy to the other side, and here there is a reflection of energy. So, here there is a incoming wave. In this case we know, assume that the nature of the incoming wave is known, and knowing the nature of the obstacle, we require to determine the nature of the two outgoing waves. So, this is known, nature of the incoming wave is known, and here we are interested, these are unknowns. Only what happens here, we only assume that the nature of the structure is known. So, we need to know what are the nature of the outgoing waves. So, in that case we call this as a scattering. Okay. So, with this physical understanding of a scattering problem and a radiation problem, let us see how we look into these problems in practice in the case of water waves. So, here we are all acquainted with the basic equations. Suppose I have a wave equation. Let me think of finite water depth, and this is my mean free surface, y is equal to 0, and this is y is equal to eta xt. I consider a 2-dimensional problem, fluid domain. So, my wave profile is a 1-dimensional in nature. Y becomes a function of eta, eta is a function of x and t, and this is my surface elevation. and this is mean free surface. We all know in the fluid domain del square phi is 0, and on the mean free surface, that is on y is equal to 0, which I call it as the mean free surface. Sometimes we call it also SWL, still water level or still water level. On the still water level, we have phi Tt plus g phi y is equal to 0. Phi Tt plus g phi y is 0, and here we have this is water depth is finite. So, this distance is uniform depth. This I call it as h. Here del phi by del y will be 0. This is 0, and this is the line y is equal to minus h. This I assume the depth is uniform, and again this condition is satisfied. This is on the mean free surface y is equal to 0, and we all know that phi t plus g eta is 0 on the surface, and also eta t is phi y, and these two conditions are satisfied on y is equal to 0, from which we obtain this free surface boundary condition. This is the linearized dynamic condition, this is the linearized kinematic condition, and combining these we have already got the free surface boundary condition, which is this, and this is satisfied on this surface y is equal to 0. And we have seen if we start with the wave eta is equal to a e to the power I times k x minus omega t, we have seen that the corresponding phi, or we can see that corresponding velocity potential, let me call this as capital phi. So, the corresponding velocity potential will be a g by I omega into cos hyperbolic k into h plus pi by cos hyperbolic k h into e to the power I times k x minus omega t. So, and here this omega satisfies the dispersion relation, omega square is g k tan hyperbolic k h. This is the dispersion relation. Now, if I look at this dispersion relation, what happened here? This dispersion, what about the behavior of the, if I assume that I know the period of the wave, assuming we have worked out several problems on this from the dispersion relation. If I assume that t is the period, t is known, that is wave period is known, and I know what is my water depth h, the water depth, sorry, water depth is known, and I have g is equal to 9.81 meter per second square. Then what will be my k? That I need to know. So, we have already seen that omega square is equal to g k tan hyperbolic k h. We have worked out also several problems that this has k 0 one real root in the positive real axis. So, one real root. Now, what will happen? So, and that is gives us the corresponding wave number. If k 0 is the one real root of this, this number k is equal to, if I call it k is equal to 0 one real root. So, the corresponding phi that I call, or eta I call the progressive wave solution, corresponding eta is the progressive wave part. So, for k is equal to k naught for real. So, that means this for every depth, for if once for every time period t water depth h, we have a k naught and eta f. So, that eta is equal to a cos k x, we have a k x minus omega t, we have a wave profile that exists, and also we have seen that the corresponding this, or even if the general one what I have considered just now, eta is equal to a to the power I k x minus omega t. So, this exists for a particular, a real k exists, that is k naught I t naught. What happened to, is there any other root of this relation, this dispersion relation? Again, if I will see that to analyze the roots of this dispersion relation, let me call this as the dispersion relation. if you look at this displacement, suppose I put k is equal to I p, what happen? Or if k is equal to, if I put k is equal to I p, then omega square will be minus G p tan p h. And then now I am coming back from a hyperbolic function to a tangent function, and for we know that the tangent function is a function which is of periodicity of tangent function, periodicity of tan ph, pi is the periodicity of tan ph. So, if that is the pH, that means I can always say n minus 1 into pi is less than pH is less than n pi. So, each interval each interval of a pi I can get a different pH. So, that will give me, if I look in the positive axis, so from 0 to infinity, then I will have every interval of pi I will have a root. So, that will give me, so in this process I can easily get it has infinitely many roots. So, I call this p is equal to p n, or n is equal to 1, 2, 3 up to infinity, there are infinitely many roots. So, in the process what I get, that means my dispersion relation omega square is equal to g k tan hyperbolic k h. If this dispersion relation has k is equal to k naught 1 real root and the k is equal to I p n infinitely many complex root. Sorry, rather I will say imaginary root, because it has no real part. So, in the process what will happen to the corresponding, if I look at, because I am dealing with my original equation is a Laplace equation associated with a 2 boundary condition. So, then each, suppose I have seen that my phi is equal to, I have seen phi is equal to, for if I say my eta is equal to a e to the power I times k x minus omega t, then I have seen that my corresponding phi in case of the real solution, and k is real, that is k naught, then it will be a g by I omega to the power I times k x minus omega t into cos hyperbolic k into h plus y cos hyperbolic k h, that is my phi naught. I call this as k naught, corresponding solution. And if I look at k is equal to I p n, then my phi n's will be of the form a g by I omega e to the power, I take x as 0, then I can have I, this is I k n, so that will give minus k n x minus p n x minus I omega t, and then this will give me cos p n cos p n h. So, then what will happen to this? So, these are for n is equal to 1 to up to infinity. So, I can also say, so these are also one of the solutions, this is one solution. So, all these last few classes on waves we have emphasized only on this solution associated phi, but now you see if you look into these roots, infinitely many roots, then this also is a solution. So, it has infinitely many solutions. If I look at the original problem, then that I will just briefly say, if I look at the original problem, that means del square phi is 0, my phi t t plus g phi y 0 on y is equal to 0, and this is phi y is 0 on y is equal to h. My general solution will be of this form, phi is equal to h g by I omega, I can call it a e to the power I times k naught x minus omega t plus b times I k naught x minus I omega t plus a g by I omega. I can call it sigma n is equal to 1 to infinity a n to the minus k n x b n e to the power k n x, or rather this is p n x and this is into cos p n h plus y divided by cos p n h and into e to the power minus I omega t. Now this is the general form. Now question comes, what happened, because I was dealing with I, why this term has come, and again I was here, I was taken a minus p n, why again plus p n x. So this let us explain these terms. What happened, actually these part contribute to the propagating mode solution. These parts are the local effects which we call the evanescent modes, and this is the propagating modes. Or the progressive wave solution, or call the progressive wave solution. On the other hand, these evanescent modes are often called as local solution or local effect. So now when we say these are the local effects, what happen? Suppose I am dealing with that my only x, I am dealing with the x, the domain of fluid is only positive x axis. If I am dealing with x is 0, then what will happen to this? Because if x is 0, then b n e to the power p n x, p n's are positive, so p n x will tend to infinity. So that means I am looking for a solution which will not behave on bounded solution, I am looking only for a bounded solution. So in that case my b n will be 0. But on the other hand, if I said I am looking at, if I say I am looking at solution for x less than 0, then automatically x is less than 0. So this part will tend to 0, whereas x is less than 0 means this will be positive. So n, this will be unbounded for x less than 0. So in that case, if x is less than 0, I can call it a n is 0. So that will give me another set. So that is one thing. Then coming back to these two terms, there are physically I have just defined that for a wave, these are the two refer to the progressive wave solution, and as I have told that in case of a wave, we have a, it may happen that we have a wave which is an incoming wave, and because we may have a structure or have some obstruction, then a part of the wave energy will be reflected. So here we have a wave, the nature of the incoming wave will be I k x minus I omega t, and nature of the outgoing wave some a, nature of the outgoing will be some b into the minus I k, call it k naught x minus I omega t. So if we have a problem of a scattering problem, so we may have incident wave and also reflected wave. If we are dealing with a wave, so in that case this will contribute to the incoming wave, this contributes to the outgoing waves as far as the x is less than 0 is concerned. But if x is greater than 0, then on this side the wave will be outgoing, but it is always moving in this direction. So in this case, so these are the two waves, this one will correspond to the incoming wave and this one will correspond to the outgoing wave for x less than 0. On the other hand, if we are dealing with a scattering problem, on the other hand for x greater than 0, I may have a constant c, and then my wave will be e to the power I k x minus I omega t, and that will be the type of wave which is the outgoing wave. Here I always look at it is of the form f of x minus c t, and this is of the form f of x g of x plus c t. So, this wave which is always moves in the positive direction, and this wave which moves in the, it gives basically this sign a plus or minus gives the direction in which direction the wave is propagating. So, whether it is incoming wave or outgoing wave, but this plus minus sign gives us the direction in which the wave is propagating. So, that is why here we have this one is a, although it is a minus sign, but still it is the incoming wave, whereas this is the outgoing wave, both are minus sign, and on the other hand here we have the plus sign, this is a minus sign similar to this, but this is a outgoing wave. So, this basically determine these signs, the sign of this particularly x minus c t or x plus c t type. So, that determine whether the wave is progressing in the positive direction and it is propagate always in the negative direction. So, there are two things here, whether the wave is incoming or outgoing, one aspect, the other thing is whether the wave is propagating in the positive or negative direction, that is another thing. So, when one deals with a physical problem, one has to take these two aspects into account, which direction. Suppose I say that I have a wave which is approaching from this side, then what should be my progressive wave? So, I will be have e to the minus I k naught x minus I omega t. If wave is, if I have a structure like this and my wave is approaching from the right side. So, this will be my incoming wave. On the other hand, when wave was approaching from this side, this was becoming the incoming wave, and here the outgoing wave will be of this type, some a, here some b e to the I k naught x minus I omega t. This will be my, so if the structure is there, this is the incoming wave, this is the outgoing wave, this is the incident wave, this is the reflected wave, whereas this side the wave will be propagating this way because the wave is approaching from this side, and when it approaches from this side, then this will be some of the its nature will be e to the c e to the minus I k naught x minus I omega t. So, this will be the nature of the, because this is these waves, these two waves they are propagating in the negative direction of x axis, and whereas this wave is propagating in the positive direction of the x axis. So, anything which is propagating in the positive direction will have a minus sign of this, the nature will be like this, anything which is propagating in the negative direction, the nature will be like this. So, because of that, here it is, this wave is a wave propagating towards the positive direction, this is a wave which is propagating towards negative direction, this is again towards positive direction, this is again towards negative direction, this is towards positive direction, this is towards negative direction. So, irrespective of the fact whether it is incoming wave or outgoing wave, the direction of propagation determine the positive or negative sign in the wave pattern. So, these two things are very clear perhaps now. Now, with this understanding, we will look at the full solution and determine what kind of wave it will, what kind of solution it will be. Now, if I go back again, I will just write it again, that the general form of the velocity potential, that means phi. Phi is, I have seen that this is a g by I omega, you have a e to the power I k naught x minus omega t plus. So, I call this as a 0 and b 0 minus I k naught x minus I omega t. So, if I take minus I common, I will have this. So, this is, I call it omega t, this into okay. So, this is the general form. So, if I am looking at a case 1, if I look at a wavemaker problem. Basically, I look at a radiation problem of radiation. So, if it is a problem of radiation, then what will happen? I will have only outgoing waves. So, in that case, if I say the wave is radiating energy in both the direction. So, for x greater than 0, my B 1 it is a positive direction. So, B 1 will be A 0 will be 0 on the positive side, because this is going this is going in this way. So, this term will be, so B 0 is 0, and here this side will be B n will be 0. That is, if this line is x is 0 and I have a wavemaker problem. So, the energy is only radiated. So, your B 0 will be 0, because wave is propagating only in this direction. So, this term will contribute because of this, and this term will not contribute, whereas because wave is one of the wave will exist. And on the other hand, here B n will be, because this term will be on the right side, this term will not contribute. So, B n will be 0. On the other hand, on this side for x, this is for x greater than 0. But what will happen if the wave is generated in both the direction? In this case, what will happen this here? Then my A naught will be, because wave is propagating in the negative direction. So, A naught will be 0, and whereas from these Evanston modes, I will have B A n a 0. So, for a wavemaker problem, from the general solution, this will be, this is only will be, and this is for x less than 0. On the other hand, if I look into a scattering problem, case 2, scattering problem. In case of a scattering problem, what will happen? I will have a structure, I will have one incoming wave, I will have one outgoing wave, here I will have a outgoing wave. So, this wave is the incoming wave, this is the reflected wave, this is the transmitted wave. Incoming wave, this is the reflected wave, and this is the transmitted wave. Here I, before proceeding further, I again point out phi is the velocity potential, but it is the velocity potential. But finally, what we are interested? We are interested in knowing eta x t. As I had told earlier, that many situations, because whole problem has been recast to a problem in phi in terms of the velocity potential. So, we are solving Laplace equation subject to the free surface boundary condition and the bottom boundary condition, everything in terms of phi. So, once we obtain phi, we can get eta, because eta represents, gives the surface profile, surface elevation or the pattern of the waves. Phi does not, but the coefficients associated with the basically the coefficient a 0, b 0, a n, b n, all these terms, they give us an understanding about what exactly happened to the amplitude of the waves. So, in many situations, because all these patterns k 0 we will know, because once we solve it omega square, the dispersion relation we will know k 0. But what will happen in a wave propagation problem? We need to know these constants a 0, b 0, a n, b n. If we are looking at a radiation problem on the right side, maybe we have b 0, because of the nature of the physical problem, b 0, b n is 0, and here a 0, a n is 0, but we need other conditions to finally find what are the rest of the unknowns. Similarly, what happen in case of a scattering problem? We have an incoming wave, we have a reflected wave, we have a transmitted wave. So, if I plug in here, I look at this problem. In case of a scattering problem, on the left side for x less than 0, I will have both the terms will be. So, a 0 will be, b 0 will be returning. So, they will be, so that basically a 0 will be known, b 0 unknown, whereas because this I call the incoming wave. I assume the nature of the incoming wave is known, and B 0 is the nature of the outgoing wave, amplitude associated with the outgoing wave, that is the reflected wave, that is unknown. And again on the left side x is less than 0, and out of these two, because it is x less than 0, this term, so my a n should be 0, all a n's are 0. On the other hand, if I look at in the scattering problem, if I look at the right side for x greater than 0, in the case of the scattering problem, then I will have, because I have only one outgoing wave, that is the transmitted wave, because wave is propagating from the positive side, and then in that case my B 1 will be 0, the nature of B 1 will be 0. On the other hand, in case of the Evanston modes, I will have x less greater than 0. So, I have a n's, B n's will be 0. So, this is what will happen, and of course, the left side constants, associated constant, need not be the same as the constants on the right side, they will be different, they need not be same. I will come to a exact problem next. Now, I will go to the third case, I will come, then I will come to one by one the problems. Case 3, suppose I case of reflection, I suppose I have a rigid wall, I have a one incoming wave is coming, then there will be outgoing waves. So, in this case, suppose I am taking that this is I am in the profile is x greater than 0. So, what will be a general form of phi? Now, phi will be a g by I omega into a I call this as okay, a I e to the power I k x minus I k x minus I omega t plus a r I k naught x minus I omega t, then we have plus sigma 1 to infinity we call it a n, and this a n into the minus k n x minus I omega t. Okay, there is a phi 0, I call it f 0, and then I call it f 0 y, and here I call it f n y. And what is my f n? F 0 y is cos hyperbolic k 0 h plus y by cos hyperbolic k 0 h, f n y cos k n h plus y by cos, I use the notation p n h. This is my general form for the reflection, because I have one incident wave, this is the reflected wave, and these are the Evanston modes. This is a g by omega, this is a g. So, now if these are the patterns, so suppose I say, now I will come back to another case of a problem of a wavemaker. Basically what I say, gravity wavemaker problem. In case of a gravity wavemaker problem, like we have seen in a wave tank, in a tank which generates wave in any hydrodynamics laboratory, one can find a wave tank, particularly which generates, there is a baffle attached to at one end of the tank, and that baffle oscillate and it generates wave. So, that basically almost exists worldwide in any hydrodynamics laboratory, that for model testing of various physical models, a wave tank will be available. So, at one end of the wave tank there will be a wave maker, and which will generate the waves. So, suppose I say, let me consider this problem like this. this is my free surface, this is y is equal to eta x t, and I say this is my y is minus h, y is equal to 0. Suppose there is a wavemaker here of this position is x is equal to 0, and this way I have the wavemaker exists here and it oscillates, it makes a in the but it makes oscillation phi x is ui, it is a minus I omega t, and I mean the frequency of oscillation is the same as the frequency of the waves. This is the general nature. Suppose the wavemaker oscillates, the speed of phi x is the horizontal velocity in the horizontal direction. In the horizontal direction, it makes an oscillation of this nature. And when I say phi x is of this is basically on at x is equal to 0. So, at the mean position about x is equal to 0, this wavemaker makes a small oscillation, small amplitude oscillation with frequency same as the wave frequency. Then what will happen to the wave? Then I have in the whole fluid region, I have del square phi is 0 on this side or on this side. If I say this is, so then what will happen for? As usual, my phi will be of this form, because I am dealing with only a wavemaker problem. This wavemaker is oscillating, so my phi will be a0 into the minus nature of the I k naught x minus I omega t, then f0 y plus sigma n is equal to 1 to infinity. I will say a g by I omega, this one, this is a common term, it will be throughout, f0 y plus sigma n is equal to 1 to infinity, and this will be a n into a minus p n x minus I omega t. This is minus, so this will be plus. This is for x less than 0, and if I look at what happened on the right side, if the wave the fluid is on this side, this will be the form of the phi, and if the fluid occupies on the other side, then phi will be of this form, a g by I omega, this will be some b naught e to the power I k naught x minus I omega t f naught y plus sigma some b n this is for x greater than 0. So, this will be the nature of phi, and this will be the nature of phi for this is for x less than 0, and this will be the nature of phi for x greater than 0. Now, the main problem remains, and this phi will satisfy the free surface condition, that is the free surface condition at y is equal to 0, phi t t plus g phi y 0. All this phi and this phi, both of them satisfy the Laplace equation in the fluid domain, and also they both satisfy phi y is 0 on y is equal to minus h. Here my f 0 and f n's, here there is a f n y into, and I have already told my f n y is cos hyperbolic k 0 s plus y by cos hyperbolic k 0 h, that is n is 0, and this is cos p n s plus y by cos p n h for all n is greater than 1 to positive. So, this is my general. Now, the question comes, I have one more boundary condition, that is phi x is u y e to the minus I omega t. If I substitute for phi x here, suppose I look at the positive side, let me take any one side, positive side. So, what will happen to phi x? So, phi x at x is equal to 0 gives me I cannot, I am looking at the positive direction, I k naught, that is b naught into f naught y plus, because x is equal to 0 I am calculating, plus sigma n is equal to 1 to infinity minus it will be minus k n, then b n f n y, and this is nothing but phi x is equal to 0 into a minus I omega t, that is equal to u y e to the minus I omega t. I deal with the complex exponentials, but in reality the solution will be either the real or imaginary part of the complex potential of this complex exponential function will give me the real wave part, as we say that e to the power I k x minus omega t. The real and imaginary parts are, the real part is sin k x cos k x minus omega t or sin k x minus omega t. For ease of mathematical simplicity, we always look into the complex form of the wave, and in reality when you go for real life problems, we always finally consider the real part of this. So, if this will be this, then what will happen to my b y? If I simplify further, then I get I k naught b naught f naught y minus sigma n is equal to 1 to infinity k n b n f n y, this is equal to u y. Now, I only have one equation, but what happened here? My u y I know, because I know that way the wavemaker is oscillating, I assume u y is known. I am looking at a wave radiation problem, so I know that what is the how the wavemaker, the structure is oscillating at x is equal to 0. So, if u y is known, then what happened? I have so many unknowns b naught, b n's. So, I have b n, n is equal to 0, 1, 2, these are the unknowns. I need to obtain them. So, to obtain these unknowns, what I will do? I will look at the, because this is a kind of whether you call it a kind of eigenfunction expansion, if you look at mathematically, or by it is a kind of basic simple method of separation of variable, and this leads to a standard storm level problem. So, f and y are the eigenfunctions. If I call k 0 and p n's are the eigenvalues, then I can say that corresponding f n's will give me the eigenfunctions. And since it is a storm level type boundary value problem in f n, because f n y will satisfy the differential equation f n double dash y minus plus p n square y, sorry, p n square f n y is 0, and again f n double dash y minus p 0 square f n y is 0, and both satisfy the common thing that p n satisfy omega square is g, and this is k naught, g k naught tan hyperbolic h, and again it satisfy minus g p n tan p n h. So, this is the nature of f n, and they satisfy this equation. So, these are all standard storm level problem, and it has two point because it satisfies the pre-surface condition and also the bottom condition. We have simplified the standard two ordinary differential equation comes from, and basically has come from the Laplace equation, the y component of the Laplace equation. So, anyway, so because of this they are all, so what is the orthogonality criteria? So, they are supposed to satisfy certain orthogonality criteria, and in this case we can see that this f n f m minus s to 0 dy, the beauty is that f n y f m y dy, this is 0, for m is not equal to n, and further this is equal to sin hyperbolic 2 k h plus 2 k h by 4 k. This is for m is equal to n is equal to 0, and this is sin 2 k h plus 2 k h by 4 k, sorry, p n h by 4 p n. This is m is equal to, this is for 1 2 this, and here my fm cos hyperbolic k 0 h plus y. This is cos p n into h plus y, n is equal to 0 1 2 this thing. So, here I am not taking the division by cos hyperbolic k naught y, because cos hyperbolic k naught h, or because that is only a term which will be multiplied here. If I divide it by cos hyperbolic k n h, then another term will be here cos hyperbolic square k n h, and here cos hyperbolic cos square k n h. Only if I add here, this is the general thing. If I take f n y is this, then f m f n will be this, and this is what I rather call it f n bar and call it f n bar, and where my f n y will be f n bar y by f 0 y by cos hyperbolic k 0 h, and my f n y will be my f 0 f n bar y divided by cos k n h. So, this will be my f 0 f n. So, since once these are orthogonal, automatically f h 0 f n's are orthogonal. So, that gives us the beauty of this and this you will utilize, because my original equation, if I use I k 0 b 0 f 0 y minus sigma n is equal to 1 to infinity k n, sorry, p n b n f n y is equal to my u y, and if I apply the orthogonality of this, then I will get my b 0 as minus s to 0 u t cos hyperbolic k 0 s plus by s plus t dt, and b 0 will be I, okay, b 0 will be divided by how much I k 0 into I call it is C 0 0, and again b n will be minus s to 0 u t cos p n into s plus t d t divided by k n c n n, and this c n n, whereas c 0 0 is, I call it sin hyperbolic 2 k 0 h, sin hyperbolic 2 k 0 h plus 2 k 0 h sin hyperbolic 2 k 0 h by plus 2 k 0 h by 4 p k 0 and CNN. And only one term if I have here, if I will have cos hyperbolic term, a division term here, if or here if I have a division by cos p n h, then automatically I will have a square term will be cos hyperbolic square p n h will come, otherwise it is remains the same. This is the general form. So, this is my b 0, this is my b n, this is my c 0 and this. So, I know now all the unknown constant b n's, and what was my original equation? My original expression for phi, my original expression for phi for x greater than equal to 0 was phi x y was of this form a 0, rather on the right side I have taken b 0 f 0 y e to the power minus I k 0 x plus I k 0 x minus I omega t plus sigma b n f n y minus k n x minus I omega t, and this b n and b 0. Now, everything is known, rather it is called a function of x, y and t, because this is t phi is a function of x, y, comma t. So, now all b n's are known in terms of u y, because I have given b 0 b n in terms of u t, same as, because here the variable of integration is t, because so b n's are known. So, it is very simple, and in fact this is known as Havelock's expansion formula. Havelock's expansion formula. This is a very classical result, or sometimes we call it gravity, Havelock's gravity wavemaker problem. It is called the gravity wavemaker problem. In fact, this problem was first developed by Havelock in 1929, and it was published in philosophical magazine. Philosophical magazine, and this problem has a wide application today, and nearly in the last 90 years, last more than 80 years, this problem has helped to simplify large varieties of problem in gravity wave associated with the gravity wave or wave structure interaction problems, and almost this concept is used in the development of the wavemaker, classical wavemaker, which is used often worldwide in a tank in a hydrodynamics laboratory. With this, today I will stop, and tomorrow or in the next class rather we will talk about how the energy relation is coming into picture and how the scattering problems can be handled in simple cases. More complex situation will be handled case to case, but at least the general philosophy with the radiation and scattering problem will discuss in brief. Thank you today.